Here's a question that we were working on before. So line passes through this point. And what I was trying to say to you, Darren, you asked a question earlier on, is that this is this. So that's much more smooth. So I have a, a position vector, which ends up at 3, 2. So let's say this is 3 on that axis and 2 on this axis. So I have a point that I have a position vector that looks something like that. And what we're doing is we're saying it has to pass through the point 5, 3. So 5, 3, there's 2 on this axis here. 5, 3 would be somewhere down here. So what we're going to do is we're actually going to take this vector, right, and shift it down to this point down here and also scale it. And when I say scale it, we're scaling it with a t value, right, or any letter you like. And scaling it allows you to be able to reach to any point that you like. So it's going to have the slope, which is defined by the 3, 2. So this 3, 2 is really going to give you the slope of the line. If you put the 2 over the 3, that would be the slope of the line. But it has to pass through the point 5 minus 3. So what you're going to do is 5 minus 3 is somewhere over here, actually. What you're going to do is you're going to take this line right here, and you're going to shift it. It has the same slope as it has right now. You're going to shift it so it goes through this point right here. That's essentially what we're doing. Hopefully that makes better sense now. Right? So that 2, 3, that 3, 2 right there is not a point on the line. The 5 minus 3 is a point on the line. The 3, 2 is really giving you an idea of the slope of the line, right? That's a vector which gives you an idea of the slope of the line. Okay, so I'm going to write now the vector equation, and then I'm going to determine whether these points are on the line. Now, to write the vector equation, the way it's normally done is one of two things. You're either going to say that you can use any letter you like. We'll use, I don't know, we'll use Q. Some people put the brackets XY to represent the vector. Either one is going to be a vector, right? So let's just say that in both cases, it's equal to the point, which is the 5, 3. I'm not always going to use both of these. I'll probably just use the XY. The point 5 minus 3 plus some parameter t's, and that's the scalar that I'm talking about, which multiplies by this vector 3, 2. 3, 2. So I'm saying that as I scale this, as I change this t to different values, right, and I add on this other point over here, what I'm going to get is every single point that's on the line, right, is going to be reachable by just simply changing the t value of this. Okay, so that would be what we call the vector equation of the line, right? Now, another way that we can express this, and that will be probably good for me to just introduce it now, for us to determine whether the point 17.5 is on the line. So we're not saying y equals mx plus b, because instead of using a y-intercept, we're basically using a point on the line. Could it be any other point on the line? Absolutely. It doesn't matter which point you choose as long as it's a point on the line. So we're using the point 5 minus 3 as the point that we know that's on the line, plus we're adding on another vector, which is the t, some scalar, times the 3, 2 vector. The 3, 2 vector is the thing that gives the line its position. So we call that the position vector of this equation, basically. All right, so we're asked now about whether these points are on the line. If this was y equals mx plus b, I know what you would do. You would plug in, partially make it easier, yes. What you would do is you would plug in the value of the y and the value of the x and see if they would be equal to each other. But we're going to write the parametric version of these equations now, which is this. We're going to say that x equals, excuse me, the 5 plus 3t, and the y value of this is equal to the minus 3 plus 2t. And all I've done is I've just taken this x coordinate plus some scalar times this x coordinate of the vector, right? So now we have these two equations, were what they call the parametric equations for this vector equation for a line that passes through the 5 minus 3, that's the point on the line, and then it is the position vector of this vector line represents the 3, 2. That's all that is. Okay. No, they asked about the 17, 5. So here's what I'm going to do. I'm going to say since these two equations define the line, parametric equations define the line, I'm going to take the 17 as my x value and say that 17 is equal to 5 plus 3t, and see what t value is going to make that magic happen, right? So obviously 3t is equal to 12, which means that t is equal to 4. So if that's the case, I can now find my y value by saying, okay, since t is equal to 4 for this particular x value, it should be the same t value that works for the y value. So I'm going to say now that y should be equal to minus 3 plus 2 times 4. That should be the y value that I'm expecting to get when my t is 4, for it to correspond to the point that I'm looking at up here, which is the 17.5. Okay, so obviously this is equal to 8 minus 3, which is 5. So because the y is 5, this therefore means that 17.5, right? Remember using 17 as my x coordinate and 5 as my y coordinate, and going through the parametric form, right? 17.5 is on the line. Well, we can do the same thing with the other coordinate. Is minus 4 minus 12 also on the line? Now, that doesn't mean we're going to use 4 again, because it may be a different t value, which allows us to get this particular point. So what I'm going to do is I'm going to set my, again, just as how we did here, that x was equal to 5 plus 3t and so on. I'm going to set my x now to be equal to minus 4 and solve for t. So we're doing the same thing again. Minus 4 is equal to, remember it was 5 plus 3t, I think it was my x parametric version of the equation. And then I'm going to solve for t now. So that means that 3t is equal to minus 9. And therefore t is equal to minus 3. Okay, fine. So let's see what the corresponding y value should be in that case. So my y should be equal to, here's my parametric equation, minus 3 plus 2t. So minus 3, plus 2 times minus 3, which of course is minus 3 minus 6, which is equal to minus 9. So if this point was on the line, then my x value, which was minus 4, should have given me minus 9, but it doesn't. So minus 4 minus 12 is not on the line. Okay, so my therefore statement is that minus 4 minus 12 is not on the line, because it does not have the same, when you use a t value of, what is it, minus 3, it does not generate the required y value. Okay, all right, so hopefully that first one wasn't too difficult. Is everybody following what I've done so far? Let me know that you can hear me. Let me know that that made sense. Everybody okay with that? Great. Okay, let's move on then. The smartboard is working much better for me today than the whiteboard. Don't know why, but it is. Okay, so again, we talked about the parametric equations and, excuse me, and you can see the parametric equations here: x equals some x value plus t times some vector, etc., etc. And then it asks you to write the vector equation, which is this in parametric form. Well, the parametric form again would be that x is, in this case, is equal to the 4 plus, or in this case, minus 3t, and the y would be equal to minus 5. Let me just clean this up. will be equal to the minus 5 plus 70. What could be easier? So there's no one constant t for an equation. No, what the t does, Darius, allow you to generate all the points on the line. What all that t is doing, and oh, and there's one thing I'm missing out in all of these. I'm glad you asked me about the t, because I should always be saying that t is an element of the real numbers. Okay, that's something I haven't been saying, and I just see it's just this is yeah, it's just a scale. When you scale that t, it's just, when you say y equals mx plus b, for instance, Dario, what you're saying is that you can get any combination of points you want for x and y, right? Every time you change the x, it gives you a different y. So every time you change a t, you get another value of another combination of x's and y's. It's really all that t is doing. Because remember that you are able to get to any point on that line, which is why the equation is given to you so that you can just simply change a t and then get different combinations of x and y. So that's all it is. And you're probably wondering, so why do we even need this? Because the fact is that we already had y equals mx plus b from when we're in grade 9. Well, now we're doing vectors. And the other thing is that when we get into 3 space, just the y equals mx plus b doesn't work so well anymore. So that's why we had to come up with another way to express the equation of a line in 2 space, so that we could consistently be consistent with the way we present it also in 3 space. Okay, so there you go. There you go. That point is not on the line. Let me move over now to my next page, which is, oh, we just did this. So find the vector and parametric equations of the line passing through. Okay, let's think about this one now, right? Find a vector, and again, I should have said here that t is an element of R. All right, so t can be any real number that will change your x's, the relationship between your x's and your y's. Right? Anyway, let's get to example 2. Find the vector and parametric equations of the line passing through this point and parallel to the line which is with this vector equation. So here's the vector equation. Xy is equal to 2, 3, which means that this is a point on the line, and this is the position vector for the line. If the two lines are parallel, what is that telling you? It's telling you that their slopes are the same, and if their slopes are the same, then their position vectors are the same. So if their position vectors are the same, I'm ready to write my equation. So what does my vector equation look like? Well, my vector equation would be my xy is equal to, instead of the 2, 3, which belongs to the equation that we have now, I needed to pass through 7 minus 2. So I'm going to use that point. And then I'm going to say it's going to be the same position vector. Done. Except I should also say t is an element of the real number set. I keep forgetting to say that, and I should. Right? That's it. Right? Okay, so it also asks for the parametric version of the equation, and we're going to be good at this now. So x is therefore equal to 7 plus t, and my y is going to be equal to minus 2 minus 4t. Right? Again, as t's change, then the x's and y's would also change, giving you any other new point you want. So every t gives you a particular pair of x and y's. That's all it means, right? If t is 0, then the point is just going to be 7 minus 2. If t is 1, it's going to be some other pair of values for x and y. That's all it is. That's really all it is. Okay, let's keep going, because we have to get through this and Cartesian at the same time. Find the vector and parametric equations for the line passing through minus 1, 3, and perpendicular to the line x equals this, y equals that. Oh, okay. So just when you thought this was getting easier, now they're throwing perpendicular at you. What are we supposed to do with that? Well, it's not as hard as it looks, and I'm sure some of you are thinking it through and seeing that already. What do you think would be the position vector for the line that you're looking for, right? Well, what's the position vector now, right? Let's write this in vector form. So xy is equal to, so what do you think this looks like in vector form? What's the point that's on the line? Come on, folks, help me out, help me out. I need a little participation here. What is the point that's on this line that you think would have generated these parametric equations? Give me an equation. So, okay, so the 5 and the -4, good. And then I'd have the plus t, and what would be the position vector? So the -2 and the 3. Okay, I probably should have used square brackets there. Thank you, Baroka, and thank you, Daria. Okay, fine. But that's what the vector equation, and t is an element of the real number set. I need to try to remember to keep putting that in. But okay, but I need a position vector for my new equation, which is perpendicular. Can anybody suggest how I might be able to do that? I need a perpendicular position vector. Dot product, look at you. Look at you. Right. And you're right, by the way, Daria. And I'm going to use a dot product to prove it when we're done. It's actually easy because you learn about negative reciprocals way, way back. I mean, way back in grade 9, right? Like, y'all remember grade 9, right? Flip it and then change the sign. There you go. So I'm going to suggest to you that the position vector for the line that we want is probably going to be 3, 2. Can you get behind 3, 2? Does that make sense to you? Right? Does that position vector look about right? And notice that this one doesn't have a negative this time. It is +3 and +2. Now, if I wanted to prove it, go back and look at, yeah, we'll get to the point in a second. Go back now and look at what Darius said earlier on. How about if I dot these, right? So -2 and 3. If this is really right, then I should end up with 0 for my dot product, right? If these two things are perpendicular, and that's a test that you can always run because you learned dot product already. You can always run this test to see whether your position vector will give you a perpendicular line. Okay, hand going up. Who is that? Irfan, go. Okay, so what I did is I just thought back to grade 9 and I said, you remember when you were doing negative reciprocals back then, Irfan? Remember that? Okay, let's say I gave you a fraction, which is a slope, and the slope was, I'm just going to make up a number now, 7/4. What would the negative reciprocal of that be? 7/4. No, you'd have to change it to negative. Yeah, you have to change it to negative, right? Isn't that true? Okay, well, I'm doing the same thing here. I'm flipping the order of the position vector. So the -2 and the 3 get flipped. The 3 comes first and the 2 comes second. But I also change the sign. Right now, if you think about it, this position vector is going to give me a negative slope, right? Because one is positive and one is negative. So I want to have a position vector that's going to give me a positive slope if this is going to work. You see what I'm saying, Irfan? Right. And the other thing that I said that is what Daria mentioned earlier on probably makes sense. I should probably find the dot product of the two vectors. The first vector was the -2, 3 vector. That's this vector right here. And this new vector that I'm thinking should work would be the 3, 2 vector. If I dot these, right? So -2 times 3, that would be -6 plus 6, that's equal to 0, right? So all you need to do is to establish that the dot product of the vector that you are establishing as the perpendicular vector and the original vector, right? Dotting them gives you 0. And once you've established that, then you're good to go. Now, if these had both been, sorry, go ahead. Correct. Think about it that way. Absolutely. Yeah, you're welcome. So now we have that this 3, 2 vector represents a vector which has a perpendicular relationship to the original vector, which was at -2, 3. So I'm now ready to write my equation, right? Because anybody remember now that this vector, right, has to pass through the point -1, 3 and is perpendicular. Well, we already found, right? We already found what the vector, sorry, the position vector is, or the direction vector is that we needed. So all we need to do now is to write the equation. So here comes my equation. This is the vector equation 1. And what point are we going to use? We're going to use a point that we got in the first place, the minus 1, 3. All right, let me make that look a little bit more clear. So minus 1, 3. And then we're going to add on t, which is being, I need to learn to write better, which is going to be multiplied by the 3, 2. All right? That would represent, okay, let me tidy up this t here. That would represent a vector that does what we want it to do. It's a vector equation that passes through the point minus 1, 3. There's a point right there. And it's perpendicular because it has a direction vector or position vector, which is perpendicular to the one that we had before. Now it asks you for the parametric equations. Well, no, we know how to do that. So that means that x is equal to minus 1 plus 3t, and y is equal to 3 plus 2t. Very easy. T is an element of the rails. Okay? That's it. Look at what Quinn said, right? Quinn says swap the points and you also change the sign. If both of these were negative in the first place, then I'd make one of them negative because two negatives would make the slope actually positive. I'm just saying. All right, let's move on. We have quite a bit to get through. Now I'm going to go through some stuff some questions that are from the text. We're going to see if we can get through them quickly enough so that we can also get to the Cartesian version of the equation. Determine vector and parametric equations for lines containing points. No, they just give us 2 points. All right. No, they give us a point E and a point F, and they're asking us to come up with vector and parametric equations. What am I supposed to do with that? Right? I mean, we have the point, that's good, but we don't have a vector. Right? Is there any way for us to get a vector from those points? Come on, folks. Over to you. What do we do now? What's their EF? So in other words, what EF is saying, what EF is saying, sorry, what Quinn is saying, sorry, Quinn. So it would be the position vector, right? Yeah, you're on the right track. Yes, except that I can get the actual position vector. So Suruja is on the right track, right? I can get the actual position vector by using the EF vector or the FE vector. The truth is that either one would be fine, right? Because remember, you're going to multiply by a scalar anyway, and that scalar could be positive or negative and would reverse the direction of the position vector. So it's okay for you to be taking the EF vector as it is to take the FE vector, right? It doesn't really matter which of those you use. So what I'm going to do is I'm going to go with the EF vector, which means, here's my EF vector. Sorry, I need to put an arrow above that. Which means that I'm going to be taking f minus e. So 6 minus minus 1, which is 7. And 11 minus 5, which is 6. Okay. So that's my position vector. That's my EF vector. The vector that connects E and F would have components as I've just given you. 6 minus minus 1, which is 7. 11 minus 6, which is 5. There's your vector. All right. So now I'm going to write my equation. My equation would be that this is the, excuse me, sorry, this is the vector equation now. So my xy is equal to the point. Now, which point do I use? That's my question. Which point? I have 2 points here. Which of those points should I use? Should I use the E or should I use the F? I need an answer, folks. Which one should I use? It should not matter. You're absolutely right. Both points are on the line. You can pick whichever one you like. So I'm going to go with the E, and for no particular reason. So we know that E is on the line. So I'm going to go with the minus 1, 5 plus the T times, use square brackets here, 7, 6. That's it. It does not matter. I could have used the 6, 11. I could use a minus 1, 5. Does not matter. All right. So the next question is, what are the coordinates of the point where the line crosses the x-axis? Well, what do you know about that? Oh, sorry, vector and parametric. Let me put the parametric equations in as well. So that means that x equals -1 plus 7t, and y is equal to 5 plus 6t. T is an element of the rails. I should have put that for the first one as well. So set y to 0, solve for t, and then x. Does that make sense to everybody, what Quinn just said? Right? We know from working in grade 9 with this x-intercept, where it crosses the x-axis means the x-intercept, that's where you find the x-intercept, when you set y to 0. So we'll do that right now. So 0 is equal to 5 plus 6t, right? And what we're going to do is we're going to solve for t. So that means that 6t is equal to -5, which means that t is equal to -5 over 6. So at that point, you have a 0 when you set t to -5 over 6. And what Quinn just said is perfectly correct. Now I can find my x value for that. So my x value would be equal to -1 plus 7 times this t value of -5 over 6, which is -1 minus 35 over 6. And a little quick math here. This is -6 over 6 minus 35 over 6, which is -41 over 6. And so I'm going to say that my x, let me see what I asked the question. What are the coordinates of the points? I'm going to give you coordinates now. So the coordinates of the point are x value of -41 over 6 and a y value of 0. By definition, the x-intercept, the y value is 0. And that's it. That is it. There's nothing more complicated to this than that. Okay, can this equation, so to give you another equation, I notice that they're using this way of putting the vector equation with a letter, small lowercase letter, and a vector arrow above it. -15 minus 7 and t with the 14 over 3, 4. Can it also represent the line containing points E and F? So they're asking, you remember, that the line is not unique. Well, the line is unique, but the equation is not unique. Let me take that back. There isn't one unique equation for each line. Well, when we get to Cartesian, there will be a unique one. But for these vector form of the equation, there isn't a unique equation. So we're asking the question, could this equation also represent the line? Well, two things have to be true. They have to have the same slope or the same direction vector. There must be some relationship between the direction vector we have now, which is a 7, 6, and this direction vector here, which is a 14 over 3, 4. Is it possible for us to make these two things the same? Is there something I can multiply this by, which will give me this value of 7, 6 over here? That's really what we're asking, right? Can anybody think of any way that might happen? Is there anything that I can multiply this by? So 2 over 3, Quinn is saying, let's see if that makes sense. And we can talk about how he got that number in a second. So if we took this vector, 14 over 3, 4, and scaled it by what Quinn just said, which is 2 over 3, let's see what happens. That would make this become 2 over 3. Let's see if this is actually working now. Are you sure about 2 over 3 there, Quinn? Is that the right way for us to do this? 2 over 3? 3 over 2? Let's try 3 over 2. We can find out in a second what's an easy way for us to do this. So let's go with 3 over 2. Well, 3 over 2 here is going to give us 7. Hope everybody agrees with that. And 2 into 4, that's 2 times 3 is 6. The value first is what I was doing. Okay. So can we accept that these two vector direction vectors really are just scalar multiples of each other? There was a way that I could have found one by just simply scaling the other. So if I multiply, as Daria said, if I multiply this by 3 over 2, 3 over 2 times this, and 3 over 2 times that, I'm going to get that same 7 over 6. So if the two vectors are just simply collinear vectors, then they can both be used to get that point. Okay, get this line. But we still have to establish one more thing. And that is this point also on the original line that we just talked about? Right? Is the minus 15 minus 7 also on this line right here? This x equals because not only have we established that they have the same direction vector, just a scale version of the direction vector, we also have to establish whether this is supposed to be a point on the line, minus 15 minus 7, right? We have to see whether, correct, we have to see if this minus 15 minus 7 is also, so let's go ahead and do that. So we're going to use the x value of minus 15 and set it into the, remember, what we're doing is this point also on the line that's defined by these 2 points? And the line that's defined by these 2 points is this line right here, which in parametric form is this. I'm going to go ahead and see if that works for minus 15 minus 7. So here we go. So minus 15, that's my x value, is equal to, going back to the original equation here in parametric form, minus 1 plus 7t. So minus 1 plus 7t. Add that over here, I'm going to get minus 14 is equal to 7t, and therefore t is equal to minus 2. We're going to test that out on the y value now. So that means that at that point, my y should be equal to, here's my parametric form here, 5 plus 6t. So 5 plus 6 times minus 2 is equal to minus 12 plus 5, which is minus 7. Okay, so let's see now. So we're going back and looking at that point. It looks like minus 50 minus 7 definitely is on that line. All right. So once you've established that the point that you had, excuse me, the point that you have on this vector equation is also on this line that joins these 2 points together, and that they have the same direction vector, right? Which is a 7, 6, then we know that that's right. Now, another thing that you could have done if you wanted to figure this out and see if they have the same direction vector is just simply put the 4 over the 14 over 3 and see if when you reduce that down, you get the same thing as the 6 over 7, right? That's another thing. That's another way that you could have seen whether these direction vectors are the same. In other words, the ratio of this y to this x, 4 over 14 over 3, is the same as a 6 over 7, putting this y over this x. So that's something I think I wanted to point out to you as an alternative way for you to show that the two vectors, the two direction vectors are the same. All right, I don't know yet whether everybody is sort of following along what we're doing. Let me check with a few people. Karis, how about you? Irfan, I see your hand up. Let me just check a few people here. Jahanzeb, how about you and Karis? Does what we're doing so far kind of sort of make sense? Okay, how about Jahanzeb? Okay, perfect. All right, great. So Irfan, go ahead, please. The 3 over 2. Well, the truth is that let's put it this way. Let me put it to you this way. The easier way for us to establish that these two things, and probably what he did is he took excuse me, there's this 14 over 3 here and this 7 right here. If you were to divide these out, you probably get that 3 over 2 from. But I think the best way to do it is to do the following. Because all you're really trying to do, Irfan, is to establish whether these two things have the same basic vector. So this is 6 and 7, or 7 and 6. This one is 14 over 3 and 14 and 4. So here's what I'm going to suggest to you. See this 14 over 3 and 4 here? I'm going to go down here and put the 4 over the 14 over 3. Now, what's the best way for me to reduce that down? If I'm dividing a fraction with another fraction, do you remember how to do that? If I'm dividing, okay, so 4 times 3 over 14. Okay, so let's reduce this down. Excuse me. So we're going to end up with 2 goes into this and 14, 7 goes into that. So you end up with 6 over 7. You see what we're saying here? Right? And if you go back to this position vector that you were trying to make it equal to, it was the same 6 over 7. So that might be the easier way to figure out if two position vectors are the same, right? Because you know you put the same 6 over the 7. Yeah. What's that? Correct. Correct. The same ratio. Yeah. Sure. Yeah, 6 on top, 7 on the bottom. Same thing here. Oh, okay. I didn't get a different value. We set minus. Okay, so we're trying to see if, let me take you back up to the top. We are trying to see if, for us to establish that this version of the vector equation would be the same that connects these 2 points together. So we got this equation right here, right? This is the equation we got by finding the position vector between E and F. That was the 7, 6. And then we put the minus 1, 5 as one of the points. We could have used 6, 11, by the way. It doesn't matter. But then once we did that, and we're asking whether this other vector equation would be equivalent to this one, we have to first of all see, does it have the same direction vector, which we're saying yes. Its direction vector can be broken down into 7, 6 as well. And I think you accept that now, that this 14 over 3 and 4 could, okay. Now we have to prove that this point is also on the line. So what we did is we took the minus 15 and set it equal to the x in this parametric equation here. So x equals whatever this is. And when we did that, we found that the x that we got from that was minus 2, when you set it equal to minus 15. So let's use that minus 2 now and get the corresponding y value, which turns out to be minus 7. So it means that the minus 15 minus 7 point is on this other line that we had before. You see what we're saying, Irfan? Okay, no problem. Yeah. All right. You're welcome. I love those questions, by the way. Love those questions. Let me see if we answered everything on the previous page. Can the equation, yeah, I think we did. Okay. Determine the vector equation for the line that's perpendicular to this and passes through that point. Well, we've done something like this already. Right? In fact, I'm almost wanting to pass this up. And in fact, it's almost the same as, I mean, if it is the same as the one we did before, we're not going to do this again. 4, 1 and minus 3, 2. Hang on a second. Well, not quite, because we didn't get it in the same format. All right, so let's just do it. I have to go now. Okay, Ali. All right, no problem. I guess you can watch the video later on. Okay, so what we're getting from that, excuse me, let's see what Daria has. So 6, 5 plus T, 2, 3. Absolutely, right? All Daria did is he took the minus 3, 2, flipped it around and changed the sign, and that gives him, so we can say xy, or just, as you put there, q equals. So xy is equal to the 0.65. That's the point that's on the line, plus t times the flipped version of this, which is the negative reciprocal version of that, which is 2, 3. We're not going to spend any more time on that, folks, unless anybody wants me to. Okay, let's go. Line has the vector equation, and they give you the vector equation, find its Cartesian equation. Let's work through this now. So I'm going to write, first of all, the parametric equation. So x equals, we know how this works, minus 2 plus 7t, and y is equal to 5 minus 3t. Okay? All right. So remember now what we said is if we isolate the t, and yes, I don't have to put t as an element of the real numbers. We know that already. If we isolate the t in this case, then the first equation becomes x plus 2 divided by 7 is equal to t. Just confirm that for yourself, okay? Add 2 to the two sides and divide by 7. There's your t. And my y is going to become y minus 5, excuse me, divided by minus 3. That would be my t as well. And again, all I'm doing is I'm taking the y equation and I'm isolating the t. So I'm going to minus the 5 and I'm going to divide by minus 3. So I think everybody's okay with that. Set these two things equal to each other now. So I have x plus 2 over 7. I don't know why I need brackets, actually. That's ridiculous. I don't need brackets. So I have x plus 2 over 7 is equal to y minus 5 over minus 3. And what we're going to do is we're just going to cross multiply. So that would be minus 3x minus 6 is equal to 7y plus 35. Okay. Okay, I think that everybody should be okay with that. Or is it plus 35 or minus 35? Sorry, before somebody points that out, let me fix it. 7 times y, 7y, 7 times minus 5, minus 35. Okay. So all I'm going to do now is I'm just going to put everything together on one side, and then we have our standard form equation. So I'm going to have 7y plus 3x. All right, I'm putting everything on the right side. I'm going to have minus 35 plus 6, which would be, I guess, minus 29 equals 0. I'll double check that because I've often made mistakes. 3, so minus 6, 7y, minus 35. Add the 3 to the right, so that's positive 3x, and the 7y, and then minus 35 plus 6. I think I'm right. I think I'm right. So the traditional thing is to write the x's first. So I'm going to have 3x plus 7y minus 29 equals 0. Now, it would not have mattered if I had chosen a different point on this line. I would still end up with the same Cartesian equation, the same standard form of the equation. Now, I want you to notice something. Look at the 7 and the minus 3, right? This 3 and the 7, they look like they could be related somehow to the original 7 and the minus 3, and they are. These two are actually, if you took if you made the 3 and the 7 into a vector, right, 3 comma 7, and you were to multiply the two together, you'd actually get 0. So it looks like, and I'm telling you, this is a shortcut that you can use. It looks like what would be called normal to this equation would be the same coefficients that you would use in the standard form version of the equation, the 3 and the 7. So all you need to do is you need to flip these around, change the sign, and you're off to the races. But you're asking, so how am I going to know what that constant is on the end? Well, we're going to get to that, right? But that's a shortcut that you can always use to find the Cartesian equation, right? And it's a standard equation. Doesn't matter what point you use. Doesn't matter whether you scale this thing or not. You're going to end up with the same equation, the same Cartesian equation, the same standard form equation. So here's what we're going to do. We're going to put this in Cartesian form. That's what we want to do, right? So I'm going to ignore it. It does say slope-intercept form. That's not what we're going to do. We're going to put this into Cartesian form, all right? So we have one point on the line, which is at 3 minus 6, and we also have a position vector of minus 1 and 4, all right? So here's what I'm going to do first. I'm going to go ahead, and I'm going to do this by doing, I'm going to go in both ways for this, right? Which is to show you that you can do it the way we just did it before. Then you can also use that shortcut that I just spoke about a while ago. So going the long way first, we'd have that x is equal to 3 minus, basically minus t, and y is equal to minus 6 minus 4t. All right, and then I'm going to isolate the t. All right, so that means that, let's see the best way to do this now, that t, if I add t onto that side, is equal to, let's just say 3 minus x. All right, I'm adding the t to one side minus the x from the other. And that in the second case, that I'd have y plus 6 being divided by minus 4. All right, hopefully I haven't lost anybody there. All I've done is I've isolated the t for both of these. All right. I'm going to go ahead now and set them equal to each other. Oh, by the way, this one here didn't need me to divide by anything. I think you'd appreciate that because there was, there's no coefficient on the t whatsoever. So that's why I just had 3 minus x. So what I'm going to do now is I'm going to set them equal to each other. So 3 minus x is equal to y plus 6 over minus 4. Maybe I can't get to the angle thing. Maybe we'll do that tomorrow. But we'll just continue with this. Put this over 1. We cross multiply. We're going to get minus 12 plus 4x is equal to y plus 6. Okay, hopefully everybody, if I made a mistake, please let me know. I'm multiplying this side by minus 4, so that's minus 12, and that's plus 4x. And then if I were to bring everything onto one side, I'm going to get 4x minus y. Let's see now, that would be minus 12 minus 18 equals 0. I'm going fairly quickly, so I am depending on you to correct me if I'm messing up on any of this. Excuse me. So that 4 and that minus 1 that we're getting here, that looks awfully a lot like this here. Now remember, this is like a positive slope, right? The minus 1 and the minus 4 means you really have a positive slope. So really what you want to do is get one that only one of these is negative, which we've done. This is positive, this is negative, and then we flip the numbers around, 4 and minus 1. So there is my equation in standard form. Now, what if we had said, you know what? I don't want to have to go through all of that, right? I already know that the minus 1 minus 4 is going to give me the x and the y, the coefficients of the x and the y as the opposite of this, which is 4 and 1, and one of them has to be negative. So why don't I go ahead and say, okay, I'm going to use 4 and minus 1, right? So it's going to be 4x minus y plus some c value is equal to 0, right? So this is the shortcut method now, right? I'm going to use 4 and minus 1. And where am I getting 4 and minus 1 from? I'm flipping these around. And because these are both negative, I need them to only have one negative and one positive. So I did that. So 4x minus y plus c is equal to 0. How am I going to get the c? Can anybody help me out to get that c in the 3 minutes that we have left? Anybody? Is there some way that I can get that missing c that I don't have for this equation? I'm using that shortcut of saying that this represents the coefficients of the n. Plug in a point. Do we have a point? Do we know a point here? Quinn, is there a point that we know? Look at the equation. Look at the equation again. The 3 minus 6. Perfect. So we're going to say that 4 times the 3 minus, I think it was minus 6, minus 6 plus the c should be equal to 0. Just bear with me, folks, here. So that would be 12 plus 6 plus c equals 0. So c is equal to minus 18. There we go, right? There we go. So we now have the equation again. The 4x minus y minus 18 is equal to 0. So there's a shortcut, right? As long as you recognize that the coefficients of this, the standard form equation will be the normal. Normal means that it is at right angles to the original direction vector of minus 1, minus 4, you can make your life so much easier. All right. So since we have like 2 minutes, let me just quickly get to this one here. Determine the acute angle formed at the point of intersection created by the following pairs of lines. So what I did in this little diagram here is I put the position vectors on here. So there's a position vector at 3, 4, that's up here, and a position vector at minus 1, 3, that's here. So these two position vectors, I had two position vectors for these two. The truth is that these points don't matter. The 2, 2, and the 5, 1, treat them as if they were both position vectors coming from the origin. And they're asking what is the angle that's formed between them? How would I find that angle? Okay, we won't necessarily get the angle, but how would I get the angle between these two vectors? Is there something that we learned already? We can use a dot product. We absolutely can use a dot product. So we know that the cosine of the angle between them is going to be equal to the dot product between, I won't finish it, but I'm just going to start it, between -1 and 3, dotted with the 3, 4, all over the magnitude of the -1, 3, times, not dotted, but times, I just use another thing, the 3, 4. And that's it. And that's all.